we're going to finish up mass spectrometry by talking about mass analyzers. Oops, that pen doesn't work. Let's try it. Okay, so the mass analyzer is a critical part of the instrument because that's what's going to separate it based on this mass to charge ratio. And so this is based on sort of a physics principle. And the principle is this, that all ions in our source are given the same kinetic energy. And so from physics, you can remember this, right? Kinetic energy is equal to 1/2 mv squared, where m is mass and v is velocity. Well, again, if we're going to be moving around ions, we can also move them with voltages, electric fields. And so we end up with another equation that we can also write for kinetic energy, and that's equal to Z times E times big V, different V than this one. And so Z in this case is charge. E is a constant. That's just the charge of an electron. So that's a constant. And then big V is whatever voltage is applied. So I said we can move our ions around by applying voltages, and by doing that, we're giving them all a kinetic energy. And so if we look at this part, 1/2 mv squared is equal to ZeV. That's useful then in mass spectrometry. Now in mass spectrometry, what we really care about is the mass to charge ratio. So let's solve for that. If we put Z over here and put everything else on the other side of the equation, m over Z is equal to E times V, I have a 2eV over little v squared, right? So we can look at this, that there's some ratio of the voltage that's going to affect what velocity it goes. So if you were going to make a detector then, using this kinetic energy information that I just gave you, the detector that you might come up with is this. We'll start all our ions here, and then we'll detect them here at the end, right? So if I start all my ions, it's like a race, right? Let's see who can go first, right? And then you can race down, and we can look at the time to get the detector, right? And different ones with different mass to charge ratios, if this V is constant, will have different velocities. So the time, right, to reach the detector depends on the velocity, right, which is proportional to that mass to charge ratio. Okay, so that's we could do. This type of detector is called time of flight. Sometimes it's called TOF. It's used in some specific applications, and it's widely used in some of the biomolecule stuff today, but we don't actually have that one in our lab. But it's the easiest one that you could come up with. The one that we have in our lab is called a quadrupole. This one uses a little bit more physics. Okay, so imagine 4 poles. I'll put a diagram up of this because I draw it pretty poorly, quite frankly. But imagine 4 poles, like so literally metal rods going, and you sort of have 2 on the top going down and 2 on the sides going down. So it's really hard to kind of draw, but we have 4, they're kind of diamond shaped. Think about it like that, metal rods going back. And so what we're going to do is between 2 of these rods, we're going to kind of apply a DC voltage, and between the other 2 rods, we're going to apply an AC voltage. So remember, AC voltage is like a sine wave, one that moves, DC voltage is constant. Don't worry, the instrument does all the voltages for you. And so the main idea is that this is a mass filter. If we have a molecule, And we have a molecule that starts out, and then at the end over here, we have some sort of detector. And so the name of the game is that the analyte needs to make it through to the detector without touching a pole. And if your analyte starts here and then it touches a pole, it ends up not being through. And it actually goes through, if you were to look at the photo, it actually goes through in a sort of sinusoidal manner in the middle. And so if it makes it through, it's called resonant. And if it doesn't make it through, if it hits one of the poles, again, if you hit a pole, you're out because your charge gets neutralized. And so the non-resonant ions are not detected. And so you can set which ones of these are resonant, what mass to charge ratio is resonant, by you basically apply different voltages. And that's what sets which mass to charge ratio will get through. So both of our mass specs in our lab, we have a GCMS and an LCMS. Both of them have a quadrupole. It's a really pretty cheap detector. It's pretty rugged, but there are some limitations to it. It doesn't have, not the best, it's really not the best for resolution. So we don't have high resolution mass spectrometry, sorry, not in your second year level lab. The other thing is that that quadrupoles, so by not the best resolution, I want to explain that just a little bit more, that it means that we can't differentiate things that are like to the 3 or 4 decimal places, like I told you in the last lecture that we could do. So the M over Z's, are good, but not to lots of decimal places. The other limitation on a quadrupole is that it can only separate things that have an M over Z of less than about 3,000. So if we have a huge molecule that has only one charge on it, let's say, so 20,000, a biomolecule or something, we're not going to be able to see that with a quadrupole. But everything we're going to look at in this lab is a small organic molecule, and so we're going to be able to see that really well with the quadrupole. All right, so there's a new type of instrument that's coming around that we don't have in our lab, but I want you to kind of hear about. What's the future of mass spectrometry, or it's really the now? So what they do with mass spectrometry is often this. Now, imagine I have 3 quadrupoles all in a row. So this is quadrupole 1, and this is quadrupole 2, and this is quadrupole 3. And I'm no longer drawing all four poles because I just can't figure out how to do that. I wasn't good at it the first time. So you make your ions, and your ions start here. And at the first quadrupole, what you do is you end up choosing one mass to charge ratio that you want to look at. And this is actually called choosing the parent ion. All right, so you choose one ion. You say, I want to look at ion, let's say, that has a mass to charge ratio of 446, something like that. In the second quadrupole, then what they do is they introduce a gas. And so when you introduce a gas, it's the reason mass spec is done in a vacuum. If you introduce a gas, you'll get what's called collision-induced dissociation. Basically, your gas will hit your analyte and you'll break some bonds. So if you have enough energy in your gas, hit an analyte, break some bonds. So then you get fragments, and that's what you want to do. So you know the molecular weight because we chose it over here. Then we cause fragments. So in here, again, we get fragments out. And then what we do for the quadrupole number 3 is that we scan the mass to charge ratio of those fragments. So we say, what are the mass to charge ratios that we would get of the fragments? This instrument's, not surprisingly, called a triple quad. There are 3 quadrupoles. But what we just did is called either tandem mass spectrometry or MS-MS. And so the tandem mass spec or MS-MS, again, you choose one ion and then you fragment it. And this helps substantially with analyte identification. Because just many things can have about the same, again, to the resolution of just one quadrupole, many things can have about the same molecular weight. You start fragmenting it though, and then you can tell by the fragments what you're looking at. So this is what a lot of people do in mass spec. As I said, we don't have a triple quad in this class, but you can really understand kind of the power of mass spectrometry and the sort of future of identification, and that's what they're doing with these triple quad mass specs.